Now we can consider an example of product between two matrices. For instance, let's consider matrix A, which is equal to 1, 2, 3, 4, and matrix B, which is equal to 1, 2, 3, 4, 5, 6. We want to compute the product A times B. Is it possible? Yes, we can check that the number of columns of matrix A is 2 and the number of rows of matrix B is also 2. So it's possible to compute the product between A and B. Is it possible to compute the product between B and A? In this case, the number of columns of B is 3 and the number, but it's other than the number of rows of matrix A, which is 2. So it's not possible to compute this product. Now we can try to compute the product. We know that the final results will be a matrix with the number of rows of matrix A, which is equal to 2, and the number of columns of matrix B, which is equal to 3. So we know that we have these elements in the matrix, so a 2 by 3 matrix. In order to compute each element, we start considering the first row and the first column, and we need to compute the following operation. So the first element will be equal to, applying the formula we have seen before, is 1. It's better to compute the algebra. So if this is matrix C, the element C11 is the element C11, C12, C13, C21, C22, C23. So the element C11 will be equal to 1 times 1 plus 2 times 4, which is equal to 9. Then we consider the element C12. The element C12 is given considering the first row but the second column in the matrix. So will be given by 1 times 2 plus 2 times 5, so will be equal to 12. Then we consider the element C13, so we need to take under consideration the first row in matrix A and the third columns in matrix B. So the element C13 will be equal to 1 times 3 plus 2 times 6, so it will be equal to 15. Then we consider the second row of matrix, so we need to consider the second row of matrix A, and C21 will be equal to, consider the second row and the first column in second matrix, so it will be equal to 3 times 1 plus 4 times 4, so it will be equal to 19. Then we consider C22, so second row, second column, C22 will be equal to 3 times 2 plus 4 times 5, so it's 26. Finally, we get the C23 considering second row and third column, so C23 will be equal to 3 times 3 plus 4 times 6, which is equal to 33. So our final matrix C equal to A times B will be the matrix 9, 12, 15, 19, 26, 33. So this is the final matrix. Consider the product between matrix A and matrix B. We can consider also vector in order to perform product. So If, for instance, we consider the column vector 1, 2, 3 is a vector because it's composed just by a single column, and the row vector, which is, for instance, 2, 3, 1, consider just one row, can we consider the product U times V, U times V? Try to think by yourself and then stop the video and you will see the solution in the next in the video. Now we can see the solution. It's possible to consider this operation because the number of columns of the first matrix, which is a column vector, is 1, and is equal to the number of row of the second matrix, which is a row vector, is equal to 1. If we want to compute these results, the final results will be a matrix with the number of rows of the first matrix, which is 3, and the number of columns of the second matrix, which is 3. In order to compute this matrix, we consider the first row and the first column, so 1 times 2, 2. Then we consider the first row and the second column, so 1 times 3, which is 3. The first row and third columns, so 1 times 1 is equal to 1. Then we consider the second row, so and we multiply by the first, the second, and the third column. So the first column is 2 times 2, 4. The second column is 2 times 3, 6. The third column will be 2 times 1, which is 2. Finally, we consider the third row and the first, second, and third column, so 3 times 2 will be equal to 6, 3 times 3 will be equal to 9, and 3 times 1 will be equal to 3. And this is the results of the product between U and V. We can also compute the product between V and U. Try to think by yourself to the solution and then go away in the video. First thing we have to do is to consider if it's possible or not to compute the product between V and U. And it's possible because the number of columns of V is 3 and is equal to the number of columns, is equal to the number of rows of U, which is also 3. And the results is the matrix, which has the number of rows of first matrix, matrix V, which is 1, and the number of columns of the second matrix, which is also 1. So it's 1 by 1 matrix. It's a scalar for the final results. In order to compute this scalar, it's convenient to write again vector V equal to 2, 3, 1, and we want to multiply this vector by column vector U, which is 1, 2, 3. We need to consider the first row and the first column. So the results will be 2 times 1 plus 3 times 2 plus 1 times 3. So is the scalar 2 plus 6, which is 8, is the scalar is the scalar 21. So it's also possible to compute the product between two vectors, a column and a row vectors, and you can get also scalar as a result of this operation. Now we can consider an important topic in matrix algebra, considering the set of vectors v1, v2, vn. So we consider n vectors, maybe row vectors or column vectors. So n row or column vectors. In this case, we can get we can see that we can say that these n vectors are linearly independent if and only if no one of these vectors can be expressed as a linear combination of the other vectors, of the other n-1 vectors. In the same way, these n vectors are said to be linear dependent if any one of these n vector can be expressed as a linear combination of the other n-1 vectors. In order to understand, let's consider the following examples. We have three column vector, very simple, the vector 2, 6, which is the vector 1, then we have the vector 2, which is 1, 4, and the vector 3, which is 7, 18. So you can try to understand if these two vectors are linearly independent or dependent. It's not so easy, but it's true that if we consider the scalar 5 multiplied by 1 minus the scalar 3 or plus the scalar minus 3 multiplied by the vector 2 is equal to the vector 3. It's very easy to see that, because in this case we get vector 3 considering the scalar 5, the scalar minus 3, and adding these two vectors. In this case, so these three vectors are linear dependent because each one of these three vectors can be expressed as a linear combination of the other two vectors. We can also write 5v1 minus 3v2 minus v3 equal to 0, where 0 is not a scalar, but is very important to consider that is a vector. Is a vector 0, 0, because in this case we are considering not just scalar but vectors. Another way to say that to explain linear dependence or independence is given a set of vectors v1, v2, till n, they are said to be linear dependent if there exists a set of scalar k1, k2, until kn such that the sum, so the sum for I going from 1 until n for k1, ki multiplied by vi is equal to 0, where 0, also in this case 0, will be the 0 vector. Also, for instance, in this case, we have three scalars other than 0, which are 5, minus 3, and minus 1, and which gives 0 if we compute the sum of each scalar multiplied by each single vector. This means that if it's possible that the sum for it going to from 1 until n of ki y is equal to 0 only if ki is equal to 0 for each I. In this case, the vectors are linear independent because the only combination or the only set of scalar that gives the vector 0 is given by the scalars 0. So in this case, we can say that the the vectors are linear dependent. This is crucial to understand the concept of the topic of linear independence, because it's crucial in order to solve linear systems.